So I would like to start with the theorem of Hanser and Muich. So they work over Q in their paper, and they say, okay, so take two positive integers m1 and m2. Let me denote their sum by m. And in GLM, take the parabolic subgroup, maximal parabolic subgroup. Oh, this is small. Okay. Okay. So I consider the group GLM over the adels of the rational numbers. In GLM, take the maximal parabolic subgroup whose Levy part is GLM1 times GLM2, so the standard parabolic subgroup. So let me denote it by P sub M1, M2, and take the induced representation from two determinants. So here you take the determinant on GLM1 raised to the power S, then determinant on the other block, and form the Eisenstein series attached to this parabolic induction. Let me write the section with notation F sub S, and then, yeah, F sub S is enough. So for real part of S is sufficiently large, is given by the convergence series. Let me denote the vector of M1 and M2 by M underline. And take the analytic continuation of this Eisenstein series, and then the theorem is that the poles of this Eisenstein series, as the section varies, are locked both at the right half plane. Yeah, Marcella Hanser and Goran Muich is an organizer of this conference. Are given, obtained at the points m over 4 minus I over 2, and I, the index I, is an integer 0, 1, 2, up to the minimum m1 and m2 minus 1. This is exactly the set of poles of this Eisenstein series in the right half plane. And their proof was by analyzing the constant term along the Borel subgroup. It's a sum of many intertwining operators, and there are many delicate issues of analyzing the poles of the local intertwining operators. And more complicated is that there are many pole cancellations, and you have to sort this out. And I will show a generalization of this theorem with a set of completely different ideas. So the ideas are also a topic of this talk. Simple, sorry. They are all simple. I didn't mention it. Everything I'm talking about is a joint work with David Ginzburg. So in order to state the generalization, let me recall the definition of a Speh representation. So now we'll take F a number field. And A will be the ring of its adels. Let tau be an irreducible, unitary, cuspidal, automorphic representation of GLN-A. So I will denote by delta of tau r. R is a positive integer. It's the automorphic representation of GLN-R A. And it is obtained as a multi-residue of an Eisenstein series of the Eisenstein series on this group GLN-R attached to the parabolic induction. So you take tau and twist it by determinant to some complex power, Z1. Again, tau twisted by complex power Z2 of determinant, R times. And at the point R minus 1 over 2, R minus 3 over 2. Each time you subtract 1 until you get to 1 minus R over 2. This is an irreducible automorphic representation of GLN-R, and I will call such a representation a Speh representation. And Moglen-Walz-Purget proved that they generate the discrete non-cuspidal part of L2 for GLN-R when you fix the central character. That one of tau. Okay? So I'm going to consider the following parabolic induction. Take a Speh representation. I will call it of length M1, twisted by determinant to the S. The Speh representation of the same tau, another length M2. And take the parabolic induction to GLMN A from the standard parabolic subgroup Let me denote this parabolic induction by rho with index delta write tau, and then M underline is the pair of M1, M2, and the complex parameter S. Okay? And let me consider an Eisenstein series attached to this parabolic induction. I will denote a section by F sub tau, M underline, it's the pair M1, M2, and the complex number S. And for real S sufficiently large, given by this series. Let me write for short M underline times N. And this is the theorem I want to talk about. Ginzburg and myself. The list of poles of this Eisenstein series for real S greater or equal to 0 is given by exactly the same numbers. When real S is greater or equal to 0, they occur at S equals M over 4 minus I over 2, and I is between 0 and the minimum of M1, M2 minus 1, and all the poles are simple. And I want to talk about the main steps of the proof, because the ideas are quite different than, as usual, analyzing the constant terms. Because we know that the poles of the constant terms along the parabolic where this Eisenstein series is concentrated will give me the poles of the Eisenstein series, but it's quite complicated due to the reasons I mentioned before. In particular, how do you deal with pole cancellations? So we had a postdoc, Zhu Zhang, in Tel Aviv, and he stated this theorem for f equals the rational numbers, and he tried to follow the proof of Hanser and Muich. But there are gaps, the poles of the local intertwining operator as well. Not handled properly, and in any case, I'm going to present different ideas of the proof. What else? Another remark that I want to say is that these points, if you do a little calculations, are exactly the points where the segments 1 minus M1 over 2 minus S up to M1 minus 1 over 2 plus S. Take the same segment with M2 instead. If you take S to be positive half integers and check when do these segments are linked, It's exactly these points. So, yes? Sorry, again? Yeah. Yeah. Oh, I'm sorry. Yeah, you are right. You are right. According to the parabolic induction. And there is a clear analog if you go, for example, to the p-adic setting. Instead of tau, take a supercuspidal representation of GLN F, where F is a p-adic field. You can construct the analog of this Speh representation locally. What do? You take this parabolic induction at this point exactly, and it is known that it has a unique irreducible quotient. So let me define this unique irreducible quotient as the Speh representation of the supercuspidal sigma of GLN RF. Take this parabolic induction at the p-adic setting, then follows from Bernstein-Zelevinsky that this parabolic induction is reducible if and only if these segments are linked. And these segments are linked exactly at these points. So it makes sense, right? That these are the poles. So let me sketch some steps of the proof. So I will start by pointing at the maximal possible pole of this Eisenstein series. So by the theorem, it is obtained when I equals 0. Okay, so the first theorem that we proved is that S equals M over 4 is the maximal possible pole. And it is simple. This is relatively easy, and it works by analyzing the constant term along the parabolic where the representation is concentrated. So let me denote a parabolic subgroup of GLN M by denoting the partition of the blocks in the Levy part. So it is M times. Right, just. So when you do this, it's easy to locate the maximal possible pole. You see, when you write it as a sum of intertwining operators, that beyond it to the right, it is always holomorphic. You just see it. And you see that this pole, when it occurs, it is at M over 4. And it is simple. And it's easy to see that it is obtained by picking a section where, say, at one p-adic place, it is supported in the open set. So this is easy, relatively easy. This one? You can write the constant term. It's a sum of many intertwining operators. You can write the intertwining. Yeah, yeah. And this parabolic subgroup, so you have to take the Weil elements coming from this. There are many. Yeah. Yeah. Oh, yeah, there are cancellations. There are many cancellations, but the maximal pole is not cancelled. This one, just m over 4.
At this point, there are
No, at this point, no. No, actually, there are many elements which give this pole, but also the open cell gives this pole. So you can isolate it. Hmm? For the others. Or for potential poles that don't appear in this list. Yeah. And this is the problem. All right, so the next step is that we are going to consider a Fourier coefficient of this Eisenstein series formed exactly the way Bernstein-Zelevinsky derivatives are formed. And we regard the application of this Fourier coefficient as a sort of descent, which will take you from this parabolic induction to a similar parabolic induction, but M1 and M2 become smaller by 1, each one. Okay, so now let me write this Fourier coefficient. So consider the following unipotent subgroup. So here this size is 2n because it's GLMN. And in this block, I write the standard maximal unipotent subgroup of GL2n. Okay. So let me just denote it by Z2n. So Z2n has the form 1, x2, x2n minus 1, other coordinates. And consider the character. So I will denote it by psis sub Z2n. This part. And this is psi, the Whittaker character of Z2n. Psi of x1 plus x2 plus x2n minus 1. And psi is a non-trivial character of A modulo F that I fix once and for all. Let me denote this unipotent subgroup by y2n. And I regard this character as a character of y2n. This is exactly the character with respect to which the p-adic setting, Bernstein-Zelevinsky, take Jacquet modules, and they call it a derivative of, I don't know, rank 2n. There is an analog where you can do the same thing with, where you put the Z2n here. I will use it. You can do this too also. And then when you apply this Fourier coefficient, let me call this character psi of y2n as a character of this group with Adel points. And denote by d psi 2n the application of this Fourier coefficient to an automorphic form on GLMN. So take an automorphic form phi on GLMN and apply these Fourier coefficients. Soon I will put G here. So this is the integral of y2 and a modulo y2 and f of P y I y to n inverse y dy. And as usual, we like to think of this Fourier coefficient as a function on the stabilizer of the character in the Levy part. So I will take this subgroup of elements in the Levy part, G in the upper block, identity in the lower block, and G is in GL m minus 2n. And it is an automorphic function of G. So I regard this as an automorphic function of G. But this is really the global analog in terms of Fourier coefficients of the Bernstein-Zelevinsky derivative of this order. So I think of it as a kind of descent which associates to an automorphic form phi on GLMN, an automorphic function on GL m minus 2n. And I want to apply this to this Eisenstein series. So the theorem is that d psi 2n takes the Eisenstein series to an Eisenstein series of the form using the similar notation well, there is also a small twist, but it doesn't do by determinant to the power n minus 1. And we can write an exact formula for the section of the new Eisenstein series on the smaller group. So for real S is sufficiently large, this is sum over GL m minus 2n modulo the parabolic m1 minus 1, m2 minus 2, n. And there is a section which I'll denote by lambda of f tau s. And the lambda of f tau ms is a section for the parabolic induction, but with m1 minus 1 instead of m1 and m2 minus 1 instead of. So lambda. So it is a meromorphic section, may have poles. Of rho, according to that notation, m1 minus 1, m2 minus 1, s, and there is a small twist by determinant. It has analytic continuation. To the whole plane, and it is holomorphic when real S is greater or equal to M2 minus M1 over 2. So from now on, I'm going to assume that M1 is greater or equal to M2. If I want to, in case M1 is less than M2, I will use this other Bernstein-Zelevinsky derivative. So it all works. So usually, M2 is less or equal to M1, so this is not a positive number. So it's a good enough domain. Now, let me describe. It has a very nice Eulerian integral expression, and I can describe it as a composition of three simple operators. So this is composition of three operators. First operator, when we consider our section in this parabolic induction, let me compose it first by taking the constant term of GLM1n applied to this Speh representation with the parabolic subgroup which has blocks M1 minus 1n and n. And do the same here. So I will denote this constant term by C sub the parabolic subgroup. Apply to the first factor from the induction data. Then do the same with the second factor. And compose with the section. And now I have to erase. So this first step, it takes us the section to the following parabolic induction. I'll write just the inducing data. Delta tau M1 minus 1 times determinant to the power S minus 1/2 times tau determinant to the power S plus M1 minus 1 over 2. And with the second factor, So this is the first operator. The second operator is the intertwining operator, which flips the two middle guys. So apply this intertwining operator. Okay, I will not write the words, so it takes me to, yeah. Yeah, I said it, I didn't write it. And the third and final operator is to take Whittaker coefficient for these two. So you see the meromorphic continuation in this way, and it's easy to see the other stuff. But also it the intertwining operator which flips the two. No, the whole thing, but here it fixes this. When you write the vowel element, you flip these two. Yeah. Okay? Huh? Yeah, for the middle group. Right. This also exhibits lambda f as a decomposable section if you take f decomposable. So I can write lambda as a tensor product of local lambdas. Well, maybe I'll just say some of the things and not write them to save time. And next we prove that when we take at one place the analog of lambda at that place and regard it as a map from this parabolic induction at that place, right, to the new parabolic induction at that place. So at finite places, this map is surjective. And Archimedean places, we can show that the map has a dense image. So with lambda, locally, I can achieve all sections practically for the new parabolic induction at the lower group. So when I have information at the lower group, I can gather information at the upper, at the previous step. Okay? So I will not write it down, but I said that just to save time. All right, so let me just write it as d of psi 2n of E f tau m underline s g equals Eisenstein series of lambda f tau m underline s. Yeah, and g is in GL m minus 2 NA. Okay, so now I'm going to do the following. I have one pole for sure for the Eisenstein series, and it is the maximal pole m over 4. I take the maximal pole on the right-hand side, and I get a new pole for the left-hand side. Okay, so I know, so what is the maximal pole for the right-hand side? The M1 is now M1 minus 1. The M2 is now M2 minus 1 over 4. This is the maximal pole for the right-hand side. And this is equal to M1 plus M2 over 4 minus 1 over 2. So I get the next pole, I equals 1, because remember, this is just a Fourier coefficient applied to this. So this must have a pole at m over 4 minus 1 over 2. Right? So I have two poles. Apply deep psi 2n again. Right? So now I know that this Eisenstein series has a pole which corresponds to its m, but now with I equals 1. Right? So it has a pole because of this, of the previous step. So the left-hand side also has a pole at this point, and so on and so on. I get that all these poles, so how far can you go until you have left only one block instead of two? So it's up to m2 minus 1. Now I assume that m2 is less than m1. Okay, so this proves that these numbers, they are poles of the Eisenstein series, but I don't know their order, and I don't know yet that there are other poles. So this is the next step. So let S0 be a pole of some order E of the Eisenstein series. Take the Laurent expansion about this point. And consider the automorphic representation spanned by the leading term. So denote by pi the automorphic representation obtained by the span of the leading terms. And now let's apply the derivative or descent again, but to this new representation. So there are two possibilities. So the first one is the easy one, that you don't get a zero representation. So if this is non-zero, then this means that the Eisenstein series I obtain in the one step lower group has a pole of order E at the point S0. By induction, E equals 1, and S0 must be one of these points. I will just talk about the initial step soon, right? So I get that the Eisenstein series for the representation which corresponds to M1 minus 1, M2 minus 1, has a pole of order E at S0. Assume I did the initial case. So by induction, E is 1, and S0 is equal to M1 minus 1 plus M2 minus 1 over 4 minus I over 2, and I is between 0 and the minimum of M1 minus 1, M2 minus 1, minus 1. But this is M over 4 minus I plus 1 over 2, and I plus 1 over 2 is between 1 and M2 minus 1. So it's good. right? Now, the initial case is when the sum m1 plus m2 is the minimal, it's 2. And then the parabolic induction is from two cuspidals, tau times determinant to the s, tau times determinant to the minus s. And this is a known case. Saidi, for example. We know the poles of this Eisenstein series. Only s equals 1 over 2, 1/2. So the initial case is easy. So the problem now is, what about the possibility that this descent or derivative is 0? How do we deal with this? Too high. So the last case the last step in the proof is the case where deep psi 2n of pi is 0. So now I have to consider important orbits which are associated to Fourier coefficients on the representation, and they have the partial order, and to see what is the maximum nilpotent orbit that supports a non-trivial Fourier coefficient. So I don't have time to give the specifics of that, but nilpotent orbits in GLN are given by partitions of n. So in this case, we prove, so the notation is that O of pi is the set of maximal nilpotent orbits that afford Fourier coefficients that are non-trivial on pi. And in this case, if we know this, we show that the partition n times is the maximal partition whose Fourier coefficients is non-trivial on pi. Okay? And to write the Fourier coefficient in this case is very simple, so I'll just write it. So I have to write the unipotent group and character associated here. So it's this. So psi is a fixed non-trivial character of A modulo F. You take this unipotent radical, and you take the sum of traces of the second block diagonal. But being a maximal also gives us some extra invariance property. So one can show that when you, okay, let me give a name. So let me write this unipotent radical by V. Moment, I want to check. And let me denote this character with the index being the partition. So this means that when I take elements of pi, then I apply this Fourier coefficient along the n to the m a modulo rational points. And as usual, we like to think of this Fourier coefficient as an element, as an automorphic function on the stabilizer in the Levy part. So the stabilizer in the Levy part of this character is just G, 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 G in GLM, right? Because conjugation by G preserves the traces. So I'll write this as F for Fourier coefficient. So let me think of it as a function of G and put here G, G. So because of this maximality here, one can show that actually this is an invariant function almost when you take G in SLM. Because of Schwerner, I have to write so large, so I have to wipe all the time.
Last 5 minutes?
Yeah, I mean, wiping took 5 minutes, I think. And then I started like 2 minutes late. Okay. Yeah, a little more space. Yeah, on top too. Now, what we do is that we can move from this Fourier coefficient to another Fourier coefficient when we have this property, and it is more convenient for us to work on, and enough part of this invariance is kept. So we can switch to another Fourier coefficient. It's by the technique of exchanging roots. And the new Fourier coefficient is with respect to the following group. Right, here N and here M. Oh, sorry. Let me write U1, U2, UM. And U1, U2, UM are elements of the standard maximal or unipotent subgroup of GLM. So each U is in what I called Zn. And the character that you take now is the Whittaker character on each block. So I denoted the Whittaker character by psi sub Zn, and then U1, U2, Un. So let me denote this character by chi psi corresponding to the partition n to the m. And let me denote this Fourier coefficient, say, by F2 to save time. So this Fourier coefficient also, one proves, is non-trivial on pi. And there is an explicit formula passing from this one to this one. The explicit formula has the following form. Say at 1, for example. There is some lower unipotent group, call it Y, I don't describe it. P of Y. W0 is some appropriate Weil element. And that's it. No, and here I apply the new Fourier coefficient. There is a passage like this. Actually, one is non-trivial if and only if the other is non-trivial, once we know this. And out of this invariance property, I can still keep the invariance property with G being a diagonal matrix in SLM. So here, invariance, so actually up to a character. Which comes from changing variables when you conjugate this diagonal element through Y, a specific character. Eta 0 with respect to G. But now you take G to be diagonal C1 up to Cm, such that the product, it is in SLM. Okay, I'm soon finishing. Now, note that F2 is a composition of the constant term along this maximal unipotent radical, composed with taking Whittaker coefficients on the Levy. And I can apply it to pi, which is a residue of my Eisenstein series. I can still compute this constant term on the Eisenstein series, composed with Whittaker on the Levy, but I have this extra property with this semi-invariance along these toes. And this extra property of semi-invariance just kills all possibilities, and when we do the computations, there is only one point which obeys this semi-invariance, and it is m/4, which I know about everything. This is the only pole where this descent is 0. On all other poles, the descent is non-zero, and they are all same. I could go on and talk a little about, computing this set for all these residues. Still, give me one more minute and say one more theorem which comes out of the proof. The theorem which comes out of the proof is that when I take M1 equals M2, and I take an Eisenstein series at S equals 0, so 0 is not a pole, it's not on the list. This is 0. And what is the proof? Half a minute. Okay? Take the leading term in the Laurent expansion at S equals 0. So the first term, right? Apply this deep psi to n. It gives you the same Eisenstein series, but with m1 less by 1 and m2 less by 1. I'll talk about the initial case. By induction, it is 0. Right? So deep psi of 2n at this leading term representation is 0. So I can apply this. Check the invariance. Impossible. What is the initial case? Parabolic induction from tau determinant to the s times tau determinant to the minus s at s equals 0. This is a theorem of Shahidi and Peace. So, as a result of the proof, we have these two. Okay, I'll stop here.